Hello everyone, welcome back. So today in this video we'll be talking about the effect of concentration on cell potential. So if we move away from the standard concentration of just 1 molar or 1 atmosphere for gases and see what effect that's going to have on cells, half cells, etc. Okay, so we'll begin by looking back at the effect of delta G on concentration. So this one we already know. So for any Gibbs energy, we take the standard Gibbs energy and add onto it the gas constant times the temperature in Kelvin multiplied by the ln of the concentration of the products over the concentration of the reactants as they're written on the page or as they are at that moment. Also what we've called in the past Q. So if you remember, it'll be something like if we said A plus 2B 3C. So Q would look something like C cubed. Again, taking the stoichiometric constant and putting it over there. Multiplied by concentration of air divided by the concentration of A multiplied by B squared. Okay, and what happens in this case in our products and reactants? Now we have metal electrodes and we have liquid water that comes out as one of the reactants. Well, same as before. Anything that's not an ion in solution or a gas doesn't get counted. So if, for example, let's say that our B here, that is a solid. So that's going to be our one of the electrodes. So then we just wouldn't include B in the argument. Okay. Good. So deriving the relationship between the cell potential and concentration. Since we already know that the standard Gibbs energy is equal to negative moles of electrons times Faraday's constant times the standard cell potential, we can plug that in directly into a new relationship that we might want to make for E. So delta G we had delta G standard plus RT ln Q, right? So if we plug this in here and do something equivalent, say for the non-standard Gibbs energy, then what we'd be looking at is negative ZF E not standard cell equals the negative ZF E standard, so standard cell potential, plus RT ln Q. Now we can divide out ZF for all terms, and we end up with an F that's misplaced, but that's fine. E cell, so this is the cell potential now at whatever concentration we choose, is going to be the standard cell potential minus RT over ZF times the ln of the products, concentration of the products over the concentration of the reactants. Okay, and I'll just get this out of the way. Maybe not. And this relationship that we've now laid out, this is what we're calling the Nernst equation. Okay. So the Nernst equation is what's going to let us determine the cell potential under non-standard conditions. So let's use this in an example. We have a test of a new reference electrode. So we're using the zinc half cell and the hydrogen half cell under the following conditions. So saying that we want to test the new reference electrode, so just make sure that we end up with the same value for the zinc standard reduction potential as we normally would. 0.76 is what we'd expect, right? So, and then it gives us some concentrations for the zinc, for the acid. Reminder that this could also be presented as a pH. And now we also have a concentration, or I should say a partial pressure of the hydrogen gas. Okay, so right away, let's determine, we know that the zinc half reaction, we could just look this up in a table even, but we already seen it a few times, negative 0.76 volts. It's standard reduction potential. And we also know that the standard acid or hydronium hydrogen half cell reaction is by definition 0 volts, because that's our reference standard. So our standard cell potential, which we'll need for the Nernst equation, still the standard reduction potential of the cathode minus the standard reduction potential of the anode. And this is now, we'll pick the most positive one to be the cathode. So that is our hydrogen standard at 0. So this is 0 minus 0.76. And we have our standard cell potential is 0.76 volts. Okay, so that's one element that we needed for the Nernst equation. And we'll carry on looking for others. So we also need the number of moles that are going to be in this reaction. So let's do the balanced reaction. Okay, so we have zinc is getting oxidized into zinc 2 plus and 2 electrons. And for the balanced hydrogen reduction, or the hydronium reduction into hydrogen, we have 2 electrons and 2 H3O plus going into hydrogen and 2 waters. Okay, if you want to take a pause there and balance that from scratch, so to just do the from the hydronium to the hydrogen, having to balance out all of the oxygen and the water, or and the hydrogen with acid and water, I'd encourage you to do that. But for our purposes, this might be something that is, again, is just tabulated. So we can write it down and see that we already have our balanced electrons. So that is going to be our value for Z. The 2 moles of electrons are passing to make one set of this reaction possible. Okay, what else can we do? So the next thing that we don't know from the Nernst equations, let's just zip up here and have another look. There we go. Okay, so we have the standard cell potential, we have the moles of electrons. Faraday's constant is a constant, so it's still 96,485 coulombs per mole of electrons. Gas constant. Temperature is given in the problem. So the only thing we really need now is this ln of the products over the reactants at their current conditions. Okay, so let's do that. So we know that Q is going to be the concentration of the products over reactants, which we can look at our balanced equation now and see. Yeah, let's just take a moment to try and clean that up. Oh, it's a nightmare. Okay. Nope, Still not going to do it. Okay. Well, let's wait for our screen to catch up with us and talk about what we would do anyways. So, okay. So we're going to need to balance the products over the reactants. So what are the products in this reaction? See if this will cooperate. We have hydrogen as a product. We have zinc ions. Water is a product, but because it's the liquid solvent, we're not going to include that in our concentration list. Zinc is a solid electrode, so it also isn't going to get included. And as the reactants, we've got the hydronium concentration. So we've got those concentrations laid out up at the top of the page as part of the questions. So let's just zip past that mess and we'll try it again. So, too far, here we go. So Q, we have as the products over reactants. So here now we're gonna have the partial pressure of hydrogen multiplied by zinc concentration, zinc 2+ ions, over the concentration of H3O+ squared, because that's the stoichiometry we needed for the balanced equation, so don't forget the square there. And this should really be in atmospheres rather than in bars as was given in the question. So we have 0.3 bar multiplied by, and it's going to be 1.01325 atmospheres per 1.00000 bar. Okay. So we can plug in those values. So that's 0.3039755. Let's go with the whole thing. Multiplied by 0.010 mole for the concentration of the zinc ions over 2.5 molar squared for the acid. And this gives us a value of 0.0486. And so ln Q equals -7.6286. Okay. So now we can complete the Nernst equation. I'm going to need some space for that, so let's hope that this will all play ball. Let's just go up here and try to fill it in with the one that we already had. Here we go. Okay, so for the E cell, we had a value of 0.76. For Z, we're going to fill it in with 2. And the ln of the products over the reactants, we have a value of -7.6286. Okay, let's try to write that in. 0.76 minus RT, so this is now 8.314 and 298. And Faraday's constant still 96,485. And that didn't erase all the way, so let's do this. And this should all be multiplied by -7.6286. Okay, and we end up with a value of 0.86 volts. Okay, and so that's essentially how we're going to do the Nernst equation, or how we're going to fill that out. So in all cases, you should be able to find the standard cell potential from the tabulated data. Temperature is most often given as part of the question. The moles of electrons still have to come from the balanced equation. And the trickiest part is going to be finding the value for Q, but again, use the lessons that we've been applying since really last term, and you should be able to get that part too. Everything else you've seen before in Gibbs, it's all laid out exactly the same way. It will give you some adjustment away from the standard cell potential. Whether it's going to be towards more potential or less is really going to depend on the concentration balance of the reactants and the products. Okay, so that's all we're going to do for this video. There are lots more examples in the Ox-Toby book. If you want to look for good examples to try, I would recommend it. We'll try to get the screen sorted out so I don't have quite as much trouble next time, but then we're going to be talking about Faraday's laws and going between mass and number of electrons and the charge flow. Okay, so I will look forward to seeing you then. Thank you very much.